give it. Okay, let's, I guess, so as far as logistics, let's maybe start talking logistics. I have the midterms I gave back last class. Again, they're, you know, I grade on a curve. The mean or the median was around 55-ish, okay? So if you're, you know, at 55-ish or above, that's good. You know, if you're down well below it, okay, in the 20s and the 30s, that is bad. And you have to figure out a way to do better. You know, maybe talk to me more, talk to the TAs, do something to change that. Any questions about the midterms or what they mean? Okay. Any questions? Is the final cumulative? The final will be cumulative. So you're saying, if the question is, can we forget about this material? No. There's going to be the midterm will be on the stuff, the next midterm will be on the stuff, graph algorithms, dynamic program, combinatorial search, what we're doing now. Then the final will be on everything inclusive, including there's the last unit on complexity, computational complexity, and that will cover that. Any questions about the midterm? About yes? The median is 55-ish. Okay. A few people. I made not very many scores changed by very much. You know, so nothing really has shifted. Okay. Any questions about that? Okay. So pick that up. Let me hide the papers now, just so that there's no more temptation to pick that up. Okay, any other questions about anything? So homework 2 should be in today. I'm going to pass out homework 3. I know it's available on the website. I've got the printouts. Let me just make sure I pass that out. Homework 3 is on graph algorithms. It is due after spring break. The one novelty here is that there is going to be a program that you're going to be asked to do. Basically, we'll talk today about how you find connected components of a graph. I want you to implement a simple connected components algorithm to make sure you really understand the mechanics of how you do traversal and things like that. All I want is a printout of it, just you to run the program, convince yourself you get it right, to make sure you understand the mechanics of that. Any questions? Okay, anything else, or now I think we're pretty much on time. Okay, so at this point I'd like to start the daily problem. And we've been talking in here about, you know, we started talking about graph algorithms. And so in particular last class we talked about what graphs are and why they are important. And how you represent them in a computer, because we're going to be talking about algorithms using these representations. And the two main representations that we're going to see are adjacency matrices and adjacency lists. And the problem of the day is about the mechanics of converting between them. Okay? So let's think about what was an adjacency matrix. An adjacency matrix was an n by n matrix where element I, j, was 1 if there was an edge ij and 0 otherwise. Okay? In an adjacency list, we had an array of n, 1 for each vertex, an array of linked lists. And edge ij existed if in the ith list there was an entry j. Okay? Any questions about that? So let's think about it. What is the complexity of converting between one representation and another for n vertices and m edges? How would we go about converting from an adjacency matrix to an adjacency list? Okay? Any ideas how we would do this? Yes? A nested for loop. Okay? So what you're saying is that for I equals 1 to n, for j equals 1 to n, what are you going to do? The next step, the big thing now, is something like if m sub ij is equal to 1, now you know that there is an edge ij, right? And now you would presumably call a routine that would then do insert an edge ij into your adjacency list. Does everybody see that? Okay, I know it's not written so you can read it, but that's the basic idea here, right? So what is the complexity of this thing going to be? How much time should it take to insert edge ij into an adjacency list? Okay. To insert one edge, let's start it simpler. To insert one edge into an adjacency list, how much time does that take? Yeah? To insert one edge into an adjacency list, how much time does it take? Yes. Constant. What are you going to be doing? To insert it in, okay, I'm going to go to the list I mean, there's a question of whether you're searching or not, okay? To insert an edge in there, simply, it's just a question, if I'm inserting edge ij, I'm going to be inserting an element j, okay, into the linked list, the ith linked list. That should be constant time, right? I'm just going to insert it in at the head. Likewise, I'm going to be inserting an element into the jth linked list. I'm going to be inserting a new element I, right? If I have to look to see if there is an edge there before, then I would have to take time proportional to the degree, right? But in this particular case, I am not inserting any edge. I know I'm only going to insert each edge once because each edge is represented, in principle, once in the matrix. Okay? So any questions about that? Yes?
Since we like array lists so much, can we use the dynamic array to represent a list of
Okay, so you're saying since we like dynamic arrays so much, okay, could we use it? So dynamic arrays are good if you are going to be enlarging things, okay? So let's think about a graph where, let's say you don't know the number of vertices. Let's say you're Mark Zuckerberg and you want to represent, you're a little kid in Harvard trying to build this Facebook thingy, okay? And you don't know how many people will eventually join Facebook, right? Then what you're sort of saying here is he should probably have allocated, well, how many people are there at Harvard? There's 5,000 students. I'll allocate an array of 5,000 vertices, right? But then people keep growing, okay? More and more people join Facebook. You would like to now, maybe, you're now going to want to increase this array. That's basically what you're saying, if I'm correct. Or are you confused now? Okay, so there's two separate things. Does everybody see that if I want to make a graph bigger by adding more vertices, in some sense I've got to ultimately allocate a larger array of linked lists? Does everybody see that that's one constraint that I have? Okay? So I could use a dynamic array, just to finish the idea, for this thing. And then if I am Facebook and more people keep joining, I can maintain my adjacency list structure without big problems. You're asking something a little bit different. You're saying, why is he representing, if I'm correct, why is he representing the adjacency of edge I, of all the edges associated with adjacent on edge I, why is he representing as a linked list? Maybe I could use an array here, okay, and use that instead of a linked list. Right? And what's good and bad about that? Okay? The good thing is we kind of like arrays, and so there's nothing wrong with arrays. What would be a bad thing about representing the adjacency edges here, okay, by an array instead of a linked list? Okay? Can anybody think of any limitation? Yeah? Difference in size. Part of me says, what about deletions? Okay? So the problem here is that if I think about the dynamic array that we talked about, when we had an insertion, more and more insertions, it would get bigger and bigger, right? But if you think about the edge list here, if we really have a dynamic situations, people on friendship are constantly friending and unfriending everybody. Isn't that what you guys do? Okay, you unfriend people. And presumably the most likely people for you to unfriend, I'm going to guess, are your nearest, your oldest buddies, something like that, right? And so somehow you're going to have some kind of a means. It's not just, if you're unfriending people, you need to allow the array to compact, right? Does everybody see that? That's a potential problem there. And know when you don't have somebody there, okay? So bottom line is, certainly under certain circumstances, it might not be a bad idea to represent it as a linked list, as a dynamic array, okay? On the other hand, the most flexibility would come from the linked list, and so that's why I'm going to deal with the linked list, okay? Any questions? Okay? Any other questions about this representation? Okay, so does everybody see that if I'm going to be allowing myself to insert an edge into the linked list in constant time, to copy an n-vertex, m-edge graph from the adjacency matrix to adjacency list, how much time does that take? Yeah? Is it n times m? No. Okay, yes. N squared. Does everybody see that this is dominated here? It's the number of vertices times the number of vertices times constant, right? Any questions about that? Okay. It's important to understand things on this level. There's points in the class where it's good to be able to sleep, you can sleep through and stuff like that. But this is sort of a basic level thing. And so if you don't get it, I want comments. Yes? You say n squared plus m, and I'm going to say no, okay? Why is this, okay? What you're saying is, okay, to be honest with you, what you're going to be saying is it is n squared plus m times order 1, okay? Because what you're sort of saying is that you're going to go through this thing n squared times. You're going to check this, okay? And then for each one of the m edges, you're going to do a constant time operation, right? Now, why do I say this is n squared and not that? The reason is because what's the biggest m can be in this graph? What is the biggest m can be? N squared, as I think of it, okay? Is it n squared minus 1 or divided by 2? To me, n squared. This is why I'm a big O person, right? So I know that because m is in big O of n squared, okay? M times 1 is dominated by the n squared. And so I am willing to ignore that and say that it is n squared. Does everybody get that idea? Okay? Any questions? Okay, good. Any other questions about this routine? Okay. Let's now look at another example. Clearing, kabunk. And here I'm going to talk about a different kind of representation. A representation which is fairly esoteric, but in that you don't use it very much, although there is a graph theoretic reason why I have used an incidence matrix. An incidence matrix is an n by m matrix, okay, where element ij means that that vertex I is adjacent to edge m. Vertex I is adjacent to edge j, okay? So notice that this is different. This is the number of vertices by the number of edges. I'm going to have a column for every single edge in my graph, right? Every edge has a name, okay? I mean, think about the street. Do edges have names? Well, in a street graph, edges certainly have names, right? So let's assume that every edge has a name for a number, okay, which we'll call its name, from 1 to m. We can now represent a graph by an n by m matrix where m sub ij is 1 if and only if vertex I is part of edge j. Okay? So if I have an edge that goes, let's say, from vertex 2 to vertex 7, Then for that particular edge, which is going to be some column, the second entry on that column will be 1. The seventh entry will be 1. Everything else will be 0. That is what we mean by an incidence matrix. Okay? Any questions about this representation? Okay? Yes? Okay, so it's another way to represent the graph. In general, not as useful as the ways we've talked about. So I don't want you to get excited about incidence matrices, but I want you to understand what they are, because we're going to use them in this problem, right? Here we have n. There's going to be, every row will correspond to a vertex. Every column is going to correspond to an edge. For this any particular edge in the graph, how many vertices are associated with each edge in a graph? How many vertices are associated with each edge in a graph? 2? Exactly right. Okay? So what we're going to do is say this particular edge, which goes from, as I said, vertex 2 to vertex 27, we're going to represent that edge by one of the columns, and that column is going to look like 0 because this edge is not on vertex 1. It is on vertex 2. It's not on vertex 3, 4, 5, 6, but it is on vertex 7. Does everybody see it? So we're going to get a binary matrix where there are exactly 2 row ones per column. Any questions about what this representation is? Yes? 2D bit array. Well, is it a 2D bit array? It's a 2D bit array to the exact same extent that an adjacency matrix is a 2D bit array. Right? Let's think about an adjacency matrix. That was a 2D bit array, right? Because every value of the bit was either 0 or 1. Here, every one is 0 and 1. Okay? But actually, here we know almost all the things are going to be zeros. Okay? Any questions about that? Because there can only be 2 1s per column. Any questions? So there are reasons why people sometimes care about representing things as incidence matrices. You know, one example, if you studied some graph theory, there's a thing called the line graph. And one way to represent line graphs that turns out to be very interesting algorithmically is an incidence matrix. But if you don't know what I mean, that's not at all important. Okay? What is important is you are now asked to convert an adjacency list to an incidence matrix. Okay? How would we do this? Okay, so your input now is one of these adjacency list things. Ka-chunk, list, 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 list. You want to go from that to this. How would we go about doing that? Okay? How would we construct that? Yes? Okay, so what I'm hearing is something like this. Okay, let me boops. No, not happy. Go away. Bunk. Bunk. Clearing. Okay, so what am I hearing? First thing that I'm hearing is something like probably initialize the incidence matrix. Okay? So we know we're going to have this matrix that is 4i goes from the number of vertices to the number of edges, right? We know everything's got to be 0, presumably, except that, right? So my first thing, this would be something I would go 4i goes from 1 to m, 4i goes from, j goes from 1 to n. M sub ij is equal to 0. Does everybody get that idea? Or is anybody confused here? How many people are confused? Okay. How much time would it take to initialize this matrix? If I have n vertices and m edges, yes? N times m. Does everybody agree with that? Okay. Now what I want to do is walk through my incidence matrix, my adjacency list. What is the idea here? It's going to be something like 4i goes from 1 to the number of vertices. I am now going to look at the ith list, right? And now it's going to be something like, while, I'll say probably L is equal to the adjacency list, the ith adjacency list. That's a pointer. While L is not equal to nil, meaning I haven't hit the end of that list now, right? I'm going to want to walk through that list. Ka-chunk, ka-chunk, ka-chunk. In general, each element is going to be an element j, right? So now what I'm going to want to do, while it's not nil, I am going to want to figure out what the next thing, I'm going to say j is equal to, sort of like what L points to, dot, vertex. Now I know what again, maybe I'm saying something that's sort of, I want to be obvious, and that's why it's confusing. I've got a linked list here, and each one of these entries is the corresponding, the other vertex number of my edge, right? And now I've got I from my loop index. I've got j from my linked list thing. I now want to set the appropriate 2 bits equal to something, right? What column should I be working on? I should be working on a column unique for this edge, right? I now have a new edge. So what can I do? I probably want to set some variable, edges equals 0 at first. Here I have discovered a new edge. I'm going to probably say edges equals edges plus 1. And now I know that what I want to do is m sub, the rows here is what vertex, that's I, comma edges, okay, is equal to 1, and m sub j, comma edges, equals 1. Okay? This is how I'm going to denote those 2 things that I'm modifying. How many people are with me? I get the idea they're not. Okay? How many people are with me? How many people are not with me? Okay, a few people. Okay, so what am I going to do? I am walking through all the vertices one by one of my edge list. Once I got a vertex, I'm going to walk through that list. Each entry in this list is an edge. Does everybody see that? Therefore, I've got to set a column in here and set the appropriate 2 bits to be 1. Edges is going to be what number edge am I currently working on, right? And for every new edge I see, I'm going to have to increment that by 1. Does everybody see that? That's what I'm doing here. Then what am I going to do? The endpoint is j. I have the edges array, okay, has the property that it's on vertex I and j. I'm going to be setting the ith value in this column to 1 and the jth value in this column to 1. That is what I'm doing. How many people, any questions about this? Yes?
So if you have an undirected graph and then you have the edge, it's also represented lower with the opposite?
Okay, so there's a question of is this an undirected graph or a directed graph? And what do you want it to do on the undirected graph? So this is an interesting point. The thing that she is concerned with is that I am going to be making 2 entries, 2 columns. One entry, if it was an undirected graph, because edge ij is going to be an entry, the jth entry in ith list, and the ith entry in the jth list. By doing what I am doing here, I'm going to create 2 columns for an undirected graph. Does everybody see that? What if I don't want to do that? Which is probably in reality what I don't want to do. How would I avoid doing that? Yeah?
So compared to the vertices, the edge equals to the previous one?
Exactly right. So what I would probably do is add some kind of a test over here, right? And say if I is greater than j, Then I'm going to write this column. Does everybody see? I guess I put the edges incremented in there also. But you see what the basic idea would be? If I would first do the test, is this the first time that I'm seeing that edge? Or one time that I'm seeing that edge? And that's when I'm going to write and increment my count. Okay? Any questions about that? So this way I'm only going to make one column for each undirected edge. Before, I would be visiting every edge twice. Okay? And so I would be making 2 copies. Any questions about that? Okay? What's the time complexity of this algorithm? Okay? How many times will I go through this loop? N times. How many times will I visit this while loop? Okay? For every vertex. Let's think about it. Okay? Right now, this while loop, okay, is going to be going around according to the degree of that vertex. Right? How many outgoing edges there are. Right? Any questions about that? So, that's n times the degree. This is the degree of the vertex. Does everybody see that? Okay. What is the degree of the vertex? Yeah? I could be sloppy here and say that it is, this thing is proportional, is at most, the out degree of any vertex is at most n. I could round that up, okay, and say that this would be taking n time. But you see that on a sparse graph, that is rounding it up a lot, right? Let me give you another way to count. Okay, this is actually an important thing. Okay, so I want people to take a deep breath now, okay, and this is an important thing about to happen here. Does everybody agree that you look at this nested loop, and you see this going around n times, and you see this nested loop inside going around according to degree, and you want to say the time complexity is going to be the outer loop times the inner loop. And you're 100% right. But I want to show you another way to count it. Suppose I want to count the number of times this inner loop spins over the course of the whole program. How many times will this inner loop spin over the course of the whole program? Okay? It is going to be visiting, I'm going to visit every edge twice, right? If there's an edge ij, it's going to be on the jth entry in the ith list and the ith entry on the jth list, right? What is the total amount of time this loop is going to spin? It's proportional to the sum of the degrees of the vertices, right? What is the sum of the degrees of the vertices of a graph? Yeah? It's order m. Does everybody see? In fact, what is the sum of the degrees of a vertex? It's not order n, it's exactly 2m. Does everybody see that? So when we count graph algorithms and efficiency here, we can sloppily say it is the number of things times the biggest possible number of things we're doing. Or we could say the total number of things done here is proportional to the number of edges, right? And that's what I would prefer to think about. And so the total amount of time for this code fragment is going to be order n plus m. Okay? Let's think about that. Okay, does everybody, how many people see why that is? Raise your hands. How many people don't see why that is? Okay, this is a critical thing with the graph algorithms thing. What is the complexity of something where, the paradigm that we're doing here is basically something that says, you know, for each vertex, you know, basically visit each adjacent edge. Okay? The time that this is going to take, if this is vertex I, this is going to take time proportional to the degree of vertex I. the sum of all the degrees of vertex I, as I goes from 1 to n, is equal to twice the number of edges. Okay? So this particular program, the wrong way to interpret it is nested loops. The right way to look at it is in terms of all we are doing is visiting every edge of the graph. Okay? Any questions about that? So this is an algorithm that takes order n plus m time. Okay? Yes? What is the degree of a vertex? The degree is how many edges are incident upon it. In the case of Facebook, it's how many friends do you have? That is your degree. Okay? And I guess in Facebook, the more friends, the better a person you are, or something like that. Okay? But it's proportional to the degree of it. Any questions about that? Okay? So this is, in fact, this is important to see, because this is why a lot of graph algorithms on adjacency lists are going to be linear. Okay? Because we're going to separately charge the work done to vertices and the work done to edges. Any questions about that? Okay, that's good. One question, why did I write, okay, n plus m instead of just order m or order n? Okay, yeah? Right, so suppose, let's say, we have a group of people who are distinctly unfriendly in Facebook, okay? And none of them have any friends, right? I am sure that there is a set of hermits who have registered for Facebook pages, right? And there are n of them. If they have no friendships between them, the time it would take to do this would be order n plus the number of friendships, which would be 0. It would not be order m just because we have to visit every vertex to discover that they had no friends, right? Any questions about that? So in general, walking through an edge list is something that takes n plus m time. Any questions about that? Question like, I don't see what you just said, is a good question. Any questions about that? Okay. Finally, let's go back to the last problem now. So actually, how much time would it have taken? Let's now finish the job up here. How much time does it take to convert an adjacency list representation to an adjacency matrix representation? Okay. What did we have to do? We had to initialize the matrix, and then we had to copy the ones over, right? Copying the ones took this much time. How much time did initializing the matrix to all zeros take? N times m time. So it's nm plus this thing. What is the complexity total? Nm. This is a bigger thing than this, right? So that's interesting that in this case, the more expensive thing is actually writing out all the zeros. Any questions here? That's one reason why people don't use incidence matrices for a whole lot. But let's keep going. How would we convert an incidence matrix to an adjacency list? Okay, now we have got an n by m matrix with exactly 2 columns in here. Okay? And we want to, from this, build a nice adjacency list structure. What do we have to do that? Okay? Any ideas how we would go from this adjacency list to that? Yes?
We could go through each row of the instance matrix, and then
So do we want to go through, you're saying go through each row. What is the row going to look like? It's going to have how many ones? The number of runs will be the degree of the vertex, right? But all you're going to learn really is that if you go by row, that what their degree is. It's not clear that helps you figure out the topology of the graph, right? So how do we figure out the topology of the graph? Yeah. Now if we go through this column by column, what is interesting? I will cruise down this column and find what is the edge that matters, right? The two vertices in that column, which are given by the indices. The rows, for this column, the rows such that those entries are 1s and not 0 defines the endpoint of an edge. Does everybody see that? So the algorithm is going to go something like, for I equals 1 to m, for each edge in the graph, I'm going to want to do for j equals 1 to n, if, m sub ij is 1, then I'm going to keep track of j. And then I'm going to know what the two vertices are. And then basically I'm going to insert into this adjacency list the edge, j1 and j2. Okay, because in the course of this scan, I'm going to keep track of, find what those two endpoints are. Yes?
All right, so you're saying you start with the first column, find the first one and the second one.
Yes.
You go through every element in the first column, and then you're going to go to the next column and go through every element.
Yes.
So I was going to say go through the row, find the first one, and then go to the column and find the first one. So you'd be essentially doing the same thing.
Okay, in some sense, if you look at all the columns and you look at all the rows, in principle, you're looking at the same everything. Okay? Conceptually, the idea of what we want to do is add an edge when we find it, right? Each edge is a column, okay? And defined by the two non-zero things in that column. That's why I think of it going through that way. There may be a way to, view it another way, but that's not the way I think about it. Okay? Any questions about it? So what is the complexity of this thing? Okay? We are going to be doing, it looks like, first, we also had to have initialized the adjacency matrix to nil, adjacency list to nil. Does everybody see this? Init the adjacency list. That's going to be for I goes from 1 to n. I've got to initially make all these pointers nil. Does everybody see that? This is going to take order n time to initially nil out every one of these pointers. Then I'm going to cruise through my adjacency matrix. Once I've got my two values, I'm going to insert it. Each insertion is going to take constant time, of which there's going to be a total of m of them. But the dominant time is going to be scanning this matrix, which is going to take m times n. This conversion would be order m times n. Any questions about that? Any questions about these basic manipulations with these things? Okay? Any questions? Okay, it's important you guys understand and know how to work with adjacency lists, especially. Any questions? Yes? And this thing over here, an adjacency list is an array of linked lists. That is what an adjacency list is. Any questions about that? Okay, good. Okay, so that is the basic notion of how do we represent the graph and how do we do, basically just convert between representations. Now let's start talking about things we really want to do on a graph. And the first thing that I claim we really want to do on a graph is learn how to traverse it. Okay? Graph traversal, okay, is basically means visit every edge and vertex in the graph. Okay? It's sort of exploring a graph. You have a graph, you have a vertex. You'd like to explore everything that you can reach by walking on the graph from this point. Okay? I claim that the graph traversal problems are sort of like getting out of a maze. If you view a maze as a graph, how would you, what do I mean by viewing a maze as a graph? What does a maze look like? Okay, I picture a maze as looking something like this stuff, right? You have some kind of a notion that there's sort of walls in a maze, right? And that at certain points there are branchings where there are multiple paths you can take. Do you see that you could represent a maze by being there's a vertex for every junction. There is an edge between any two junctions you can walk to. Okay? the problem of getting out of a maze really reduces to starting from where you are, walk over the entire graph systematically so you know a way to get to you discover the particular vertex that is the exit of the maze. Does everybody get that idea? So there is a connection between traversal and getting out of mazes. How many people see that connection? Or am I going too fast? Who just sees it? Who doesn't see it and wants to see it? Nobody. Okay? So our goal is going to be, how do we explore a graph completely with two goals? First, we care about correctness. We want to make sure that we visit every edge of the graph, every vertex and every edge of the graph that is possibly reachable from where we are. To get out of a maze, you have to make sure you are always going to find the exit, right? So that is the correctness issue. There is also an efficiency issue, that we don't want to visit the same vertex or edge again and again and again and again and get trapped somehow. In an ideal world, we're going to want to visit every edge, it turns out, at most twice in the course of our walking. Any questions? Now, how do people get out of mazes? Does anybody ever know any algorithms for getting out of a maze? Yes. Just what? Okay, so the idea that people usually hear is that the way to get out of a maze is you put your hand on one of the walls and keep walking along. And the claim is that if you start putting your hand on one of the walls and keep walking around, you are never going to always get trapped and visit the same place over and over again. The claim is that I will be able to get out of the maze that is this room and find the exit by keeping my hand on the right-hand wall. Does everybody see that it isn't working? Okay? What is the problem here? The problem is you've heard this story before. How many people have heard this idea of how you get out of a maze? Okay? So there is some truth in what she is saying. But do you see that it's not complete truth here, right? I am walking. My problem is this is not correct, because I am not systematically visiting everything in the room, right? And it is not efficient because I don't know how I'm going to stop, right? So those are the key issues here. Yes?
Is it because there is more than one component?
The reason, turns out, why this doesn't work is because there's more than one connected component in this sort of underlying graph that we're talking about, okay? Which, but it's a little bit, let's say it's related to that, but it's a little bit, bottom line is, this is why graph traversal is not a trivial thing. Now, has anybody ever read any myth or story about somebody who got out of a maze? Has anybody read? Yes. What did they do?
They left a yarn behind them to show the path that they walked.
They left a yarn behind them. Does everybody see? This is one thing I did not do here. You've heard about this, I guess, the Minotaur, I think, in the Greek myth. They had he spent years building up a long string of yarn, and then he left the yarn trails behind them, okay? And that was to remember where he had been. That's an important part of the search, right? Other people, you've heard about dropping breadcrumbs behind them, right? To make sure that they know where they've been, right? And then the birds come and eat the breadcrumbs and the guy's out of luck, right? Okay. These are the issues that come up in graph traversal. This is why it is not quite as simple as it seems, okay? Any questions? So what is our idea in graph traversal? The key idea is we are going to mark each vertex when we first visit it. And we are going to also keep track of what we have not yet completely explored. Okay? Part of the problem is this. You come to an entrance in a maze. Okay? You have 3 possible places you can go. If you're going to walk on that, then you can only go one of those ways. You have to remember that you have not visited those 2 things yet. Does everybody see that? You've got to remember, I've got to come back here to make sure that I visit those things. Okay? That is sort of the key idea, to make sure that I visit these things. So we're going to keep, for every vertex, we're going to keep it in, it's going to be in one of 3 states at any point in the search. One is undiscovered. This means that the graph, we have never been at this vertex before. Two is we have discovered the vertex, but we haven't actually checked out all its edges. That's our situation here. We walked along, we discovered this vertex. Therefore, we then left it now and walked down one of those paths. This vertex has been discovered, but it has not yet been completely explored. When I come back here and check that out, and then wander around, and then come back here and check that out, and explore this, now I've explored everything I can reach from this thing. And if that's true, now this is completely explored, and I say completely explored, and that I mean by processed. Any questions? Did everybody see this evolution from undiscovered to discovered but not completely explored to having completely explored it? Any questions? So, any of these search reversal algorithms work by, let's take a look at it. Okay? That work by going this thing, and for every vertex there's going to be an evolution from undiscovered to discovered to fully processed. Any questions? Okay, good. So the other part is we have the vertex labels. We also have this notion of a to-do list. Namely, during the course of our vertex, we start out on here's some graph that is totally unknown. We start at one vertex, which we know of. We look at its outer edge, and one of the edge going out is to a new vertex. We now discovered it. We're going to keep a list of the vertices that we have discovered, but not fully processed. Okay? That's a to-do list. And we're going to have to make sure that we actually do everything that is on the to-do list. Okay? So part of what we're going to have to do is maintain a data structure of what is our work that is remaining. And on one level, the entire difference between breadth-first search and depth-first search is just the data structure that you use to maintain what work remains to be done. How many people here had heard of breadth-first search before we came in here? Everybody. How many people had heard of depth-first search? Everybody, at least everybody who's awake, right? But so on one level, they're very, very similar. And on one level, they only differ by what data structure you use to maintain the to-do list. Okay? So a reasonable thing that you might have thought is, why do professors spend so much time worrying about the difference between the two of them? It turns out that the traversals have subtle properties that make them very different in very useful ways, okay, on different kinds of algorithms. Okay, and that's why we're going to spend time talking breadth-first search today, depth-first search next time. Any questions? So what is the deal? Again, with all of these traversals, the important thing is that we are going to explore, if we start from a vertex, and we explore everything in a connected, that if we are in a connected component, okay, we will in fact explore, okay, every vertex and edge of it if we do the traversal this way. Why is it? Basically, we'll start from some vertex. We are going to systematically, eventually explore all the outgoing degree vertices of it, the adjacent vertices of it. We're going to keep track of all the things we discover, and for each thing we discover, we are eventually going to explore all of its outer edges. If there is a vertex that you say, wait a second, on this graph my traversal would never get to it, if it's a connected graph, this vertex is going to be adjacent to something that is in the component. Or if it is connected, there is going to be, if you have a set of vertices you do discover, every other vertex is somewhere along the line. If the vertices are discovered or non-discovered, there is going to be some edge that spans from the discovered part to the undiscovered part. Our traversal will explore things until we have explored every consequence of everything we know. And that is why traversal is going to be correct for connected components. Any questions? Okay, good. So what is breadth-first traversal? Okay, let's look at the implementation, because I think the details here matter. Okay? In my implementation, again, there's different ways you could implement it. I don't want to say my code style is the best or anything like that. But basically, we agree that it's got to evolve. Every vertex is going to evolve from being undiscovered to discovered to processed. The way I'm doing it is I have two Boolean arrays, processed and discovered, okay? And when a vertex is, and this is, I have an entry here for every vertex in the graph. For vertex I, initially, processed is going to be false, and discovered is going to be false. When I discover the vertex, I am going to set the discovered flag to be true. When I finish processing the vertex, I'm going to set the processed flag to be true. Okay? And this is going to be how I record my state. Any questions about that? I am also, for breadth-first search, and actually for depth-first search too later on, keep track of another useful thing, which is the parent. If you think about it, in the course of discovering something, okay, every vertex, when it is discovered, there will be one other vertex that discovered it. Okay, how are we going to discover a vertex? The first vertex we are saying is given. We're then going to go and explore all the outgoing edges from it. When I explore the outgoing edge from this, if this vertex was not discovered before, now it is discovered. If I am vertex I and this is vertex j, if I discover vertex j before any other vertex discovered it, I am the discoverer of it. And the discoverer of it is going to be called the parent. Any questions? How many parents can a vertex have by this model? Okay, yeah, how many? One, it's parent, it's a discoverer. How many times can something be discovered? In principle, it can only be discovered once, right? The fact is that one vertex could discover many things. Columbus discovered many things, right? But each vertex can only be discovered once. And that means that there is sort of a tree on the vertices imposed by this breadth-first search procedure. Okay? Does everybody see what I mean? The discovery relationship is going to give us a tree. Okay? And that tree, the breadth-first search tree, is going to have properties that we care about. Any questions? Okay, ka-chunk. What is my code going to be? First, to initialize my search. For every vertex, I've got to initialize my state vertices. No vertex has been processed or discovered. No vertex has a parent. That's why I set it to be -1. That's the initialization phase of my search. The actual search, kabunk, 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 is going to look something like this. To hold my discovered but not completely explored stuff, I am going to use a queue, a FIFO queue, first in, first out. Okay? What am I going to do? I'm going to start my search. I have to start on some vertex of the graph. Let's say start is the start vertex. What I'm going to do is first go to take my queue, initialize it to empty, then say vertex 1, okay, my start vertex is one that I have discovered because somebody told me about it. I'm going to stick it in the queue of stuff that's been discovered but not completely explored, and then announce at the flag to say that I have discovered it. And now vertex 1 is start is discovered, and it is in the queue to be explored. The main thing of breadth-first search is a loop, a while loop. While there is something on the queue, take the next vertex off the queue. If I want to do something with this vertex, I have augmented my search with routines where I can do something with this vertex now that I'm there. If you think about it on a trip, you want to make a trip, you visit everything. Often you want to do something. Maybe you want to take a photograph when you're at a vertex, right? You need to have a place to actually do something. I augment my thing by generic routines to tell me that I could do something now that I am at the vertex. Once I remove it from the to-do work, I say, now I have processed this vertex, okay? Because I'm taking it off to do, I'm now going to go process it. What I'm going to do is look at all the edges coming out of vertex V. This is P here is going to tell me. These are the edges associated with vertex V. While that list is null, okay, not null, meaning that there is an entry on it. Find the other edge point of that edge by walking down. This is now, here's my linked list. Here is V. I've got a linked list for this. Y is the other endpoint. If Y has not been completely processed, then I'm going to visit this edge, and if I want to do something on this edge, I'm going to do it. Process vertex and process edge are routines I'm allowed to do when I visit that vertex. Otherwise, if I have discovered it, I'm now going to check to see, is the endpoint that I have discovered, vertex Y, has that vertex been discovered yet? If it has not been discovered, then I am the discoverer of it. Okay? And what does that mean? I am going to get noted as vertex Y has been discovered. Vertex V is the one that discovered it, so that's why the parent thing is here. I'm going to stick vertex Y in the queue of stuff to be processed later, and basically just keep looping through it. That is the breadth first search algorithm. Any questions about that? Yes?
What was the edges array? That was the adjacency list?
Yes, the adjacency list I am representing here by something called an edges array. Okay, if I look at this thing here, I have my graph G. Here it says that G is my graph, okay? And in this case, I have G points to edges. That is going to be the vertex, the array associated with the edge list representation of G. Okay? Any questions? Okay? This I recognize is boring to hear. But graph algorithms are very subtle, and it's important that you understand what is actually going on in this routine. Any questions about that? Okay? Fair enough. So if we believe that, okay, let's look at an example. What is going to happen when we visit vertex 1? We're going to have our queue of stuff we want to do. Originally, we put vertex 1 on it. All the vertices were not discovered before. Once I start searching for vertex 1, this vertex has been discovered. Does everybody see that? In the course of doing that, what am I going to do? I'm going to look at the outpost edge. Here's another edge. Vertex 2 had not been discovered before. I'm going to add 2 to my queue. Actually, I'm now exploring this, so I took 1 off my queue. And I have discovered 2. I have discovered 5. Let me put 5 on my queue. I have discovered 6. Now I have completely explored all the outgoing edges from this. This vertex is now completely explored. Okay? What am I now going to do? I am now going to start from my the oldest thing in my queue, which happens to be 2, and start searching from here. I look at the outgoing edges. 2 goes to 1, but 1 has already been explored, so that's not anything that I've discovered, right? 3 I have not done. 3 is discovered. Does everybody see that? In fact, actually, I guess one way to think of it is the discovery is filling in this tree. Okay? 2 is discovering, Okay, 2 is now visiting 5, but 5 has already been discovered. That edge is not interesting. Now I have completely explored 2. From 2, I'm now going to look at the next vertex. Okay, 3. No, next vertex is 5, because 5 is the next thing that I am told to do in my queue. From 5, I look at the outgoing edges. 5 to 2 is just going back to its discovery. Wait, no, 5. 5, its neighbors are 1, is its discoverer. Okay? There's an edge going back that way. 5 will discover 4. Okay, now 4 has been discovered. What do I now do? I go to 6. 6 here, I've looked, I've explored all of 6's outgoing edges. Nothing has happened. I now go to the next element in my queue, which is 3. I look at 3's outgoing edges. I have discovered another edge, going from 3 to 4, but 4 had already been discovered, right? Actually, let me erase that. That's not what I want to do. Okay? And then when I finish this thing, I now look at 4, all outgoing edges. Now that this queue is empty, I am done. Any questions about that? The important thing is this way I have visited every vertex in my graph, okay, and I have got a tree of discovery. Okay? Any questions about that? Okay, good. Okay? Now, in using traversal for something, note that I am visiting every vertex in the edge. If you looked at my implementation, I have places in the code where I allow you to specify your own process vertex and process edge function. This is how you use traversal for what you care about. Okay? If you want to print out the vertices of the graph, you would do it by adding the appropriate statement here. The more complicated algorithms we're going to build out of depth-first search and breadth-first search are going to work because during the unique time when I visit each edge and each vertex once, I'm going to take the right action. Okay? And so this payload is kind of really why you're doing the traversal. Any questions? Okay. Now, what is interesting about the parent relation is the parent relation describes the tree of discovery. In a breadth-first search, notice what we did. We started from one vertex, and we explored all the nodes that could be reached in one hop. Then for each one of these, we looked at all the nodes that we could reach one hop from now. This tree of discovery radiates out from the vertices so that every new vertex that is discovered, the interesting thing about breadth-first search is that the discovery relation defines the shortest unweighted path between the root and that vertex. Okay? This is an important enough thing to say again, because I can tell people are starting to doze here. Okay? Note that what breadth-first search is doing is you're starting from one vertex, and you're storing the to-do work in a FIFO queue, first in, first out. That means that every time you pull work from the queue, it is going to be the oldest thing, the oldest discovered thing. Does everybody see that? So originally, that means basically all the vertices that are direct descendants of the root are going to get explored before any vertex that is 2 hops away. That means that any discovery of things that are reachable from these vertices will be made by a vertex that is a distance 1 from the root, rather than this vertex, which happens to be 2 distances from the root. This vertex might also be adjacent to there. But there's no way for this vertex to discover that vertex, because this one is a distance 1 from the root, and this is ka-chunk, 3 from the root. Does everybody see that? So the interesting thing about breadth-first search is that this parent relation defines the shortest path from the root to everybody else in an unweighted graph. Any questions about that? How many people see why that should be? Okay? How many people don't see why that should be? Okay? This is, in some sense, the biggest sales feature of breadth-first search. Okay? Is that breadth-first search trees define a way to, to give you the shortest path from any vertex to all the other vertices in an unweighted graph. Okay? That's the important point here. It's the shortest path using the smallest number of edges. Okay? So if we have an unweighted graph where every edge has a weight 1 in some sense, the smallest number of edges between I and j is exactly going to be the path in the breadth-first search tree, where if we started from vertex I, we discover vertex j. If we walk backwards from the tree of discovery until we hit the root, that is the shortest path from j to I. Any questions about that? Okay? Any questions? Kind of like this to be more energetic. Okay? I can understand why it's not. But the people see why breadth-first search naturally gives this shortest path property. Okay? Because we're radiating out. We're exploring from a vertex. In some sense, you start from a vertex. We are basically sort of exploring in a spiral-like pattern out from a vertex. And whenever there is a new vertex discovered, we have always found the shortest way to it in terms of the minimum number of edges. Any questions about that? Okay? Good. Now here's a question. If we have a tree of discovery, here we have vertex I, this discovered that, this discovered that, this discovered that. How do I find the shortest path, the path in the tree from I to j? Note that the edges in the tree of discovery, each vertex is discovered once. So the edges in the tree of discovery go from a vertex to its parent. Is that right? So how would I find the shortest path given the tree discovery? How would I find the shortest path from vertex I to vertex j? Okay? If I have a tree of discovery where the edges are like this, how would I find the shortest path from I to j? Okay, yeah? What should be clear is the tree of discovery, because it points to the root. I can't go directly from vertex I to j. I can go in my tree from vertex j to I. Does everybody see that? So to find the shortest path from j to I, I'm going to start from vertex j and then keep walking back in the parent, back, until I get a parent, the parent vertex, or until this vertex, the parent of this is nil. Okay? You could do this iteratively. From here, while the parent is not nil, keep walking back. Or you could do it iteratively, okay? Recursively. But to find the actual path involves walking backwards through this tree of discovery. Any questions about that? Okay? So the bread and butter reason why we care about breadth-first search is because this tree of discovery gives me a way to find the shortest path from every vertex to the root, okay, for an unweighted graph. Any questions about that? Okay, fair enough. Hold on. Okay, give me 1 second here. Good. Kabunk, kabunk. Okay, let's now start to use breadth-first search as a component for building bigger graph algorithms. Okay? And one of the most important graph algorithm problems is that of finding connected components in a graph. Okay? What is a connected component? Here I have a set of roads. Here I have a set of roads. Okay? If it was a road map, can we drive between here and England? Okay? The answer is no. Why can't we drive between here and England? The reason is that there is an ocean. Does everybody see that idea? There is an ocean between us and England. Okay? Now, if you were to build the road network on the world, every vertex is going to be a junction. There is going to be an edge between any pair of vertices, okay, where there is a direct road between it. Do you see that there is a non-trivial question of how do you tell whether or not there is a path between New York and London? Okay? One is you find the path. Okay? But notice that, that somehow the road network naturally breaks down into these pieces where you can travel within a piece, but these pieces are separate. Okay? The problem of finding connected components is that of isolating what are the separate pieces of the graph. Okay? So you can deal with them separately. Does everybody get that idea? Now, when people hear about the connected components problem, they may say, wait a second, this looks trivial. It's obvious there's no way to drive between New York and London. They're in separate pieces. That's only because you're seeing this picture. Does everybody see that I could have, if I numbered these vertices, 1, 2, 3, 4, 5. This graph, what would this graph look like? It would have an adjacency list. Every vertex would have edges coming out of it, right? It is not immediately obvious when you look at this adjacency list that there are multiple pieces of that graph, right? The problem of finding connected components is identifying what those pieces are, okay? And this comes up in lots and lots of problems. I'll show you, before the class ends, how you actually find these things. But by far the most important thing to remember is what is it, why is it that you might want to find connected components of a graph? Okay? One reason is in a transportation network. Okay? That, again, the reason why, if you go onto Google and you ask to find a road, the shortest way to drive between New York and Pyongyang, North Korea, it isn't going to spend forever looking. Why not? Because it knows that it has pre-processed the road network, and it knows that this is in a separate connected component than that, and there is no way to drive between them. Does everybody see that idea? Why might one need to find connected components in a graph? Let's just think about this. Can anybody think on any of the graphs we've thought about why connected components might be a thing you would want to do? Okay? Yeah?
In order to determine if there's some way of manipulating a system so that it goes from some start state to some end state.
So one thing that's probably true is if you represent the state of a system by, let's say a vertex, what important thing is you're going to want to check, is it possible that from the state that comes on when you turn on the system, is everything reachable? Can you make all possible states? Maybe you've got the state in the system that when you reach it, suddenly the system becomes invisible. Okay? That would be a very good thing. But if that's in a separate connected component from where you started from, there's no way to reach it. Right? That's good. Why else might you care about connected components? Finding dead code. Remember that we would have, again, we talked about the call graph thing, where you have different parts of your program, and from certain places you can get from one code fragment to another. Disconnected components means that there is some code from here that you can't get reach from the other part. And so for detecting the problem of detecting dead code is exactly connected components. Yes, what else?
Jeff, not too curious, see if
Okay, so one thing that presumably the Lil, or what do they call them now? What's our local company? Not Keys. It's crap. Yes, that it is. It is crap. But what is the name of it again? LIPA. LIPA used to be something different. Lilco used to be Lilco, LIPA, whatever. But bottom line is, every once in a while there is a storm that comes up and knocks down a lot of power lines. And does the electric company care? Well, our company, no. But what do they really, in principle, should they care about? You will have power. If here is a power plant and here is your house, if there is a wire, a path between that power plant and your house, you will have lights, okay? And if not, you won't. So what is the algorithm that they should be checking about? Given the state of which wires are up and which wires are down, okay, is the graph connected? Does everybody have their own, is everybody connected to the grid? Okay, any questions? So there are a lot of problems that reduce to basically testing whether a graph is in one component or not. Another thing that's true is that almost any graph computation you do, okay, it turns out that, that the graph algorithms we work in here almost always assume that the graph is connected. How can you take your graph, if you have a graph algorithm that assumes the graph is connected, what should you do? If you're given a garden variety graph, like the one of here that I was walking around that had problems because it was disconnected, the first thing you should do is run a connected components algorithm. Identify the connected hunks of the graph and run the algorithm separately on each connected component. Okay? So connected components are a big deal. Okay? Any questions? A simple deal, but a big deal. Any questions? So how do we find if a graph is connected? Okay? Well, we just do a breadth-first search from a vertex. Okay? Basically, the connected components algorithm is going to look like this. We initialize the traversal. We start our search from the first vertex, for I equals 1. We then are going to do a breadth-first search, okay, from the first vertex. Anything that is reachable from that vertex is going to be part of its component. Does everybody see that? So if we start from New York and we visit every vertex that is reachable from New York, we will cover every single vertex in the United States. What's going to be left after we've done that traversal, however, is there might still be vertices that are undiscovered. If the graph was two connected components, the London vertex would not get discovered when we did our traversal from New York. So the other part of the connected components algorithm, it's basically just breadth-first search. But what it's going to do is not just start the vertex from the first part, but it's going to check every possible starting point. And if the ith vertex has not been discovered, that means that this vertex belongs in a different connected component than any vertex we've seen before. If C is going to be a counter we're going to have here to tell what connected component we're on, okay? What this is going to do is we're going to say C is 0. Then the moment we discover an undiscovered vertex, C is now bopped up by 1. This is we'll print it out. Everything we visit now is going to be part of component 1. We're then going to loop back, and if we later discover after the search is done another undiscovered vertex, that's going to be part of the next component. Any questions about that algorithm? Okay? Do people see what the idea that it is doing? It is really just a breadth-first traversal from every single vertex of the graph. Okay? Except there is no reason to explore any vertex again that has already been visited once in the course of a traversal. Okay? Any questions about that? Kabunk. Clear? Kabunk. Okay? I think I'm going to hold off on 2 columns. But the people see, make sure you understand this components algorithm. because this is something you're going to have to do on the homework. What is going to happen? You start from the first vertex. In the course of doing the traversal, bop, 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 you're going to discover lots of other vertices. Some vertices will not be discovered. And then you're going to start a traversal from the first undiscovered vertex. What is the complexity of this? If we have n vertices and m edges, what is the complexity of this algorithm? I'll let you go as soon as you answer this. Okay? All of what? When we start from this vertex, what is the complexity of the breadth first search from the first vertex? O of however many vertices and edges are in that component. Right? There could be n, but there's going to be how many are in that component. And what we're going to do is we're going to visit exactly the edges in that component there. The next traversal we do, we will visit all the edges and vertices in that component. Every vertex will be visited once. Every edge will be visited twice. The total amount of work will be proportional to the number of edges plus the number of vertices in the graph. Any questions? Okay, thanks for your attention. Look at this and we'll talk more about it next.